Hello and welcome to my presentation of the design approach for heavy-duty soft robotic gripper. After a short introduction of myself, I will show you the necessity of the design approach in the context of the fourth industrial revolution. Then I will be going over to the structuring of the design approach and in short application case and what has to be done in the future. My name is Alexander Müller and I'm a research engineer at the Technical University of Berlin from Germany. I'm working for the Institute for Machine Tools and Factory Management, IWF, especially for the chair of handling and assembly technology Hamster. The recent years I was working on soft robotic simulations for handling and assembly, and parallel to it I'm working with my colleagues on high throughput production technologies for lithium-ion batteries. So if you're interested to get more details about, so you can join us about these codes. Just take a screenshot and make a photo. And you can looking for LinkedIn, YouTube and homepage to get more details of our works. But now in the context of the fourth industrial revolution, we have an increasing personalized customer requirements and product customization, which leads to a growing variety of variants. And in a fully automated production line, we have problematic when we going to batch sizes which are getting smaller and smaller because our resources are not capable to handle this different product variants, and so we are going to a limited production problematic. So how we can avoid this problematic? We can adapt flexible resources in the fully automated production line. For this problematic, we have four options. The first principle of the flexible and adaptive handling principle is the modular principle. This means we were using a various adaptation of a basic configuration. In this case, it's a vacuum suction gripper, and it's capable to configure itself to use it for different handling objects. The next principle is the specialization principle. This means we were using custom-made gripper drawers which are mounted on conventional grippers through a suitable interface. The next principle is the cooperation principle. We're using a set of gripper or a set of industrial robots which cooperate together to handle heavy or complex parts. And the fourth and last principle is the soft robotic principle, which means we were using soft and compliant gripper drawers for different geometries and variants of the product itself. But all these handling principles have their own problematic. The first three of them are really specific principles. The modular principle means we have really long setup times when we adapt the basic configuration for each specific product. Specialization principle, we have to produce one specific gripper for one specific product variant, which results in a lot of extra costs and time. And the cooperation principle has a problematic with the synchronization of the set of gripper or set of industrial robots because it's too complex to handle it for this amount of product variants. The soft robotic principle is a really nice principle, but in general this principle is just capable for lower payloads. So my idea behind this, we have to produce heavy-duty soft robotic gripper to avoid the problematic of the limited production with small batch sizes. Before we start with my design approach for heavy-duty soft robotic gripper, I want to give you a short overview about the state-of-the-art soft robotic grippers itself. So here we see on the left side a Soft-Pneumatic-Actuator which works with pressured air. This brings the gripping fingers to curvature and then they will producing low clamping forces. In general, the payload is really low, approximately under 1 kilogram. And in the middle, we see a finger gripper system. It's really similar to the conventional 2 or 3 finger gripper drawers, but he has the property of the compliance. This means he's more flexible and can handle softer other parts. On the right side, we see a tandem-driven actuated gripper system. In this case, it's an anthropomorphic hand. It's an actuated gripper system, but in general, we have to use a set of actuators, so we have the same problematic with the synchronization principle. And we have other gripper systems which are capable to produce higher payloads, but all of them are in general just for one specific design. Or we have to test the specific design in advance. So we are not capable to use those gripper systems in a fully automated production line when we have a lot of changing product variants. This means on the left side we have a four-finger gripper, but when we say the shape of the product itself, we don't know if it will work. So we have to test it with a prototype. In the middle of the picture, we see the same problematic. We see a really specialized gripper system which is handling a round bar with a gecko surface. But this gecko surface produced adhesive forces to glue the object and the gripper system together, so it seems so, but with the release strategy with high accuracy are problematic too. On the right side, we have a really advanced jamming-based gripper system. It can handle heavy or complex parts. We are seeing how to handle a metal sheet from the automotive industry. And this jamming-based system works with a granulate-fed pillow. So we are using this granulate to interact with under-pressured air. This brings this granulate to stick together, and because of this friction, we can grasp the object. But all of this gripper system had a problematic because the simulations took a lot of time. So for this jamming-based system, this simulation is really complex, so it took a lot of time. And the other principles are just for one specific design case. So my idea behind is to use a design approach for the grip simulation that we can avoid the problematic of specific designs and automatize it for the fourth industrial revolution. But now we come to my design approach for heavy-duty soft-robotic-gripper. The design approach exists out of 4 steps. The gripper selection, followed from the material selection, the material characterization, and the grip simulation. The design approach is a really simple and effective design approach with low effort and high benefit. This is because we have to do the first 3 steps just once, and the grip simulation we can adapt on every specific design case we were looking for. But now we begin with the gripper selection. The gripper selection, you can choose any kind of gripper what you are looking for. In our case, we were going for the fin-rail gripper system. The fin-rail gripper system has a lot of advantages. One of them is we can use rigid body joints in the design process. This means we avoid single point of contact or line contact through bearings or needle rings because of the rigid joint. This means we have a uniform distribution of material strain in the inside of the structure itself, and this results in a really low weight of the gripper system itself. Another nice advantage of the fin-rail gripper is that you use the shark fin effect. This means when we're adding a gripper load on the surface of one gripper jaw, the deformation of the gripper jaw is in the opposite direction of the added force. This means we produce a bigger surface of the bigger contact surface, and this leads to a softer grip and a more damage-free handling process. When we choose the gripper system, in this case it was a fin-rail gripper, we have to looking for the correct material. In soft robotic in general, we were going for young modules between 10 to the power of 2 to 6 Pascal, which is because we want to interact with humans, and this means these young modules is in the range of the human skin and the human bone. So we avoid problematic when we get in contact between the robotics and the humans. The next important principle or requirement is that we are looking for easy processing, so easy manufacturing process itself. So the material has to be easy to produce, and this is why we were looking for material which we can print through additive manufacturing or through an easy casting process. Then of course we were looking for a low weight gripper system, so the material has to have a low density. And the material has to have a high toughness and a high ductility, because we were looking for grouper systems which are compliant, so they don't have to break when we're producing larger clamping forces, and they has to be soft enough that we will not deformate the gripping object. So in soft robotics, we see in most cases silicons, elastomers, and polyurethanes. But for heavy-duty soft robotic grippers, both of them are not capable because they are produce only low payloads because of the low young models. So we were going for polyurethane, especially the thermoplastic of them, the TPU, because it's accomplished all soft property criteria for our gripper system. After the gripper selection and the material selection, we have to do the material characterization. It's a really important process because we want to know exactly what we can expect from our gripper simulation later. So we have to going for the full process just once. Then we know exactly from our production process what we can expect. So when we're using the thermoplastic polyurethane, we have to print some samples. In our case, we use the Ultimaker 2, and we're using a 0.6 diameter nozzle with 100% infill to produce these samples for the axial tangible testing. So this material test produced our strain stress ratios. We see these curves are really similar to each other, so the accuracy of the manufacture process is really high. And when we get these results, we want to convert them to the material model to produce a simulation of the unaxial tangible test. And we want to compare these both results to know exactly how high our accuracy is. In this case, we were going for a hyperelastic material model. In my simulation tool, I can choose between a Neo-Hookean model or Octa model or Mali-River model. So which model you choose, it depends on you because your gripper has different strain rates. Our strain rate from fin-ray grippers we were testing were in the range of about 15%. That means with this specific material model, we get an accuracy of about 90–18%. So when you are not happy with this accuracy, you can do a lot of other material tests to use more advanced material models or other parameter settings to have a higher accuracy in your simulation tool. And after the material selection, finally we get to the grip simulations what we were looking for. So this is the gripping simulation what we want to adapt in our fully automated production process, because we can automatically choose the gripper system and test it in advance if we is capable to handle this object from place A to B or to assemble this specific product. So in this stage from the design approach, we were looking for specific results, what we are interested in. In some case, we were looking for the maximum contact force on the gripped object because we want to know if the gripping process will be damage-free. Or we can looking for the maximum payload capability of the gripper itself, that we know that the product variance from a really small to a really big product can be handled. And when we have these different size and shapes, we can also looking for usable gripping positions for one product, but we use different gripping positions for different sizes of the product variants. So how we came to get these results, I use a three-stage process in my grip simulation. And in the first stage, I was going for the characterization of the gripper, of the designed gripper itself. And then we use the specific data for the second stage. And this stage, we derive this results what we are looking for. And when we are not happy with those results, we have an optional third stage where we can going for an optimization algorithm, which changing the parameter settings of the gripper itself, that we produces better results what we were looking for. And this is the first stage of the grip simulation. This is the characterization stage. And here we have chosen our thin-wire gripper system with a thermoplastic polyurethane, and we have a round bar which we want to grip. So at first I fixed this round bar in the middle and forcibly closed the gripper jaws, the thin-wire gripper jaws. So because we have a compliant gripper system, the gripper will not break, so the gripper will be collapsed or will be deformed at, yeah. And this is what we were looking for. We want to look for the maximum contact force what we can produce before the gripper will begin to collapse. And in the middle of this finger gripper, of the gripper jaws, we see this little bars, it's called fins. And the fins begins to buckle if the contact force is too high. So we're going for the specific peak. We see it here in this bar, in this graph. And we're using this specific point as a maximum actuator force, which will close our gripper jaws. With this specific characterization, we know we can maximum use this actuator force to produce. In this case, we were looking for the maximum payload capability. So the maximum contact force from the first stage is really essential. So then I first, in the second stage, I were looking for the maximum payload capability. I fixed the object again, firstly, and then I closed the gripping finger with this specific actuator force from the first stage. So we see how the gripper fingers were closed from the first to the third picture. And then in the third picture, I will begin to pull off the gripped object out of the grasp. And I'm measuring how much force is necessary to pull it out of the grasp. And this is the result is that we can measure our maximum payload for this specific design. And in this case, we will have around 4 kilogram payload capability of this gripper design. And I thought in advance, when you're not happy with these results, you can optimize the parameter settings of the gripper and go again. And for the thin-wire gripper, I was talking about the material model. I thought that we have an accuracy about 95% because you see this deformation, this specific design case is that we have a maximum of about a 14.8% strain. So what you saw the last few minutes. In the context of the fourth industrial revolution, we're getting to a problematic because of the personalized customization problematic, because this results in a really low batch size. And when we have a fully automated production process, we have to use flexible resources to avoid the problematic of the limited production. One solution is to use soft robotic, but normal soft robotic grippers are not capable to hold higher payloads. So this is why I introduced heavy-duty soft robotic grippers, and especially the design as a gripping simulation for these heavy-duty soft robotic grippers. So I introduced you a really simple and effective design approach, which has a low effort and a high benefit, because you have to do the gripping selection, the material selection and material characterization just once, and then you can use this generic method. So you can use the grip simulations for a really fast pre-validation for different product variants, and you can easily adapt your gripping system. So you avoid a lot of time-consuming characterization through prototypes. And here are my references, most of them from this presentation you can find in my paper, and I used some of these references in this presentation from Commercial Gripper System. You can looking at them just at their home pages. Yeah, thank you for your attention, and when you're interested for more details on this topic, just contact me about my email address. You see it in the description underneath the video. So thank you.